let's remind ourselves of a few things we talked about last time. Here are the derivative rules I would like you all to make sure that you're aware of. Of course, the ones we already learned from 16A, product rule, quotient rule, chain rule, which we'll certainly come up as we talk about things. Come on in. But the new derivative rules we've learned in 16B are the following. Let me write some things down. Co-16B, today is what, the 16th? Yeah. So here are the new derivative rules that we have learned so far in 16B. That the derivative of e to the x is e to the x. And more generally, the chain rule version, which I always think of as this is the real derivative formula you should know, is that the derivative of e to some function of x is e to that function of x times the derivative of that function. Or as I would write less mathematically, the James version is that the derivative of e to the stuff is e to the stuff times the derivative of that stuff. That's what I'm always going to say, even though this is like the more like technically correct way of writing it. Similarly, we also have learned that the derivative of the natural log of x is equal to 1 over x. And again, more generally, the chain rule version, the derivative of the natural log of a function of x is equal to 1 over that stuff times the derivative of that stuff. We'll see quite a few examples here in a moment. And again, if I were saying it, I would say the derivative of the natural log of some stuff, 1 over the stuff times the derivative of the stuff. Yeah, you can put the derivative in the numerator of that fraction there. I like to write it at the end just to kind of emphasize that you're always at the end, the multiplying by the derivative of the stuff. But if you want to put it on top, that's fine. Questions about this before we do some examples? Yeah.
This was like after the after you like simplify it.
What do you mean? Say it again.
Oh, this goes like after the log equation.
I guess, yeah. So for example, if I wanted to find the derivative of, say, what have I got? I got lots of examples. Yeah, let's say the natural log of x cubed times the square root of x squared plus 1. I could do this the hard way. We could make our lives challenging and say, okay, well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff. And then I would take another step to actually find the derivative of this here. Now again, we shouldn't do it this way. You're going to see why in a second. This would be 1 over x cubed times, let's change that to x squared plus 1 to the 1/2. Just so when I take the derivative over here, it's easier for me to think about. All right, for the derivative of x cubed times x squared plus 1 to the 1/2 power, we're going to have to use the product rule. So what's the derivative of x cubed? Thank you, yes, 3x squared. And then we multiply it by the other thing left alone, x squared plus 1 to the 1/2 power, plus then we do the reverse. We leave the x cubed alone. We multiply by the derivative of x cubed plus x squared plus 1 to the 1/2, which is 1/2 times our stuff to the negative 1/2 times the derivative of the inside stuff, which is 2x. Yes, it definitely is. It's also possible, and I will attempt to make sure that I don't write so small. But again, this is not how I really want you to see how to do it. So let's actually look at the better way of doing it. I will tell you, or I'll warn you, our answer is going to look a little different because we're going to have a different simplification here. So the better way of doing this is by saying the derivative of the natural log of x cubed times the square root of x squared plus 1. We should first use our properties of logs. We can break this up as the derivative of the natural log of x cubed plus the natural log of the square root of x squared plus one, or x squared plus one to the 1/2 power. And then again, actually, before we start taking derivatives, we can use one more property and say this is equal to the derivative of 3 times the natural log of x plus 1/2 times the natural log of x squared plus 1. We broke it up using the product rule for logarithms. We brought those powers down using the power rule for logarithms. And then finally, we actually take the derivative. The derivative of 3 times some stuff is 3 times the derivative of that stuff. So the derivative of 3 times natural log of x is 3 times 1 over x. The 1/2 hangs out here. The derivative of the natural log of x squared plus 1 is going to be 1 over x squared plus 1 times what? Exactly. Is this answer the same as that answer? Yeah, but they look wildly different. You'd have to do a lot of simplifying of this. I mean, not a whole lot, but enough that it would be some work to get from here to there. We could do it, but we don't want to do it. The whole point here is that if you're differentiating something that has a logarithm, it's almost always in your best interest to simplify it as much as possible before we start taking the derivative. In fact, to that end, why don't you all try finding the derivative of the following? I want you to find the derivative of, what do I got here? Sure. The natural log of x cubed plus sine of x divided by, sure, cosine of x to the 4th power. Definitely first break it up into a couple logarithms. That's it. It's easy. All right, let's take a look. So I'm going to break this up as, I'm going to make a tiny mistake here, just to point something out. So I'm going to break this up as the natural log of x cubed plus sine of x minus the natural log of cosine of x to the 4th. And the mistake I made was I didn't write down d dx. I still have to take the derivative, so I still need to write the instruction saying that I still have to take the derivative. So I should still be writing derivative of all of that. You don't need parentheses, but you could write like big parentheses around all that if you really wanted to. Totally unnecessary though. And then I'm going to do one more simplification before I take the derivative. I'm going to write this as the derivative of natural log of x cubed plus sine of x minus 4 times the natural log of cosine of x. Sadly, I can't bring this power down in front because it's not the power on the entire argument of the logarithm. It's just the power on part of something that's being added. Basically, addition or subtraction means you're kind of stuck in the logarithm. Once you've got addition or subtraction, you can't really do anything else. So now we use our rules. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 3x squared plus cosine of x. Minus 4 times the derivative of the natural log of some stuff is 1 over the stuff. Times the derivative of the stuff is negative sine of x. If I were taking a test and they said not to simplify, I would leave it alone. I will simplify this though. Question, Nikki.
Why didn't we distribute the log into x?
So when you say distribute, so when we say distribute, what we mean is you have something multiplied by a sum. So for example, if I had just really easily 3x squared times x to the fourth plus 6x, then I could distribute because this 3x squared is multiplied by x to the fourth plus 6x. I would distribute like that, and then I get 3x to the 6 plus 18x cubed. But the question you're asking is kind of similar to asking, why don't I distribute the square root across x to the fourth plus 6x? Because it's not multiplication, it's a function of. You're taking the square root of this entire expression, just like we're taking the natural log of this entire expression. Yeah. And then just to simplify this, because we could make it look nicer, I could write this as 3x squared plus cosine of x over x cubed plus sine of x. And I could write this as minus times a minus is plus, and sine of x divided by cosine of x is going to give me tangent of x. Not super necessary to do this, but if you're trying to check answers like in the back of the textbook, it'll probably look more like this instead of like this. So it's good to be able to see how things simplify, even if you're not going to simplify them. Again, everyone, just as an FYI, right? You're always welcome to ask questions. I'm happy to explain things further, clarify, whatever, or go in more detail. I'm just trying to show you things I think you need to know. So let's look at another example. Oh yeah, question. By the way, what's your name, by the way? Andrea, what's your question? This, so like from this step to this step. So for this first part here, I have 1 over this multiplied by that, and I'm just rewriting it as that part of the numerator, because essentially I'm multiplying fractions. This fraction is 1 over x cubed plus sine x. This fraction is 3x squared plus cosine x over 1. When you have fractions times fractions, you're doing top times top, bottom times bottom. Over here, I have a -4 times a 1 over cosine times a negative sine of x over 1, if you like. And what I'm really doing is I'm just multiplying it all together. So I've got, right, this whole part here is really -4 times negative sine over cosine. -4 times negative sine is +4, so I'm going to put the 4, and I like to put the 4 out in front. And then sine of x divided by cosine of x is tangent of x. That's how we're getting there. That's it. All right, let's look at another one. Let's look at something slightly different. Let's say I want to find the derivative dy dx given the equation x cubed plus y to the fourth plus the natural log of x times y equal to 7. And even though I haven't said it at all, the way this equation is written, this problem is posed, means I'm going to have to use what method of differentiation? Implicit, right? I've got x's and y's mixed up together. I can't just solve for y. That almost always means we have to use implicit differentiation. So when we use implicit, what that means is we should first, well, usually first, although there's a small thing I'm going to do before that, but usually we first just differentiate both sides. But I'll say, just like the other problems we've done, before you start differentiating things, it is usually a good idea to use any logarithmic properties you might have. I don't want to really differentiate the natural log of x times y and get 1 over x times y times the derivative of x times y, which is going to be a product rule thing I don't want to have to worry about. So what I'm going to do first, before I do that, is first simplify. I'm going to rewrite this as x cubed plus y to the fourth plus the natural log of x plus the natural log of y equal to 7. Just to make my differentiating a little bit easier. I'm going to remind everybody, when we do this, we are always imagining that y is a function of x. So, let me go back a page for just 1 second. Let me remind everybody. I don't know, that's not ideal, James. Never mind. So now we're going to differentiate both sides. The derivative of x cubed is 3x squared. And I'm going to say the derivative of some stuff to the fourth power is going to be 4 times our stuff to the third power. But then I said stuff, so I have to multiply by the derivative of the stuff. The derivative of the natural log of x is 1 over x. I should say more words here. I should really say the derivative of x cubed with respect to x is 3x squared. The derivative of y to the fourth with respect to x is 4y cubed times dy dx. The derivative of the natural log of x with respect to x is 1 over x. The derivative of the natural log of y with respect to x is 1 over your stuff times the derivative of your stuff. And what's the derivative of 7? Right. And then the rest is algebra. We're going to solve for dy dx. So we're going to look at all the terms that have a dy dx, which is this term here, leave them on the side they're on, or take them to the other side. It doesn't matter which side you pick. And then separate them. So I'm going to have, excuse me, 4y cubed times dy dx. It's also perfectly fine to write y prime, which is usually my preference, plus 1 over y times dy dx equal to negative 3x squared minus 1 over x, bringing those other things to the right-hand side. Factor out the dy dx, so that you're left with 4y cubed plus 1 over y, still equal to negative 3x squared plus 1 over x. And finally, divide both sides by this here, whatever's multiplying by dy dx, to get dy dx isolated and equal to negative 3x squared plus 1 over x divided by 4y cubed plus 1 over y. Yeah. I mean, what I did, and I didn't show all my work here, what I did was I subtracted 1 over x from both sides. So I subtracted 1 over x here, subtracted 1 over x here, I subtracted 3x squared here, I subtracted 3x squared here. So when they moved over to the right-hand side of the equation, they became negative because I subtracted them from both sides.
But then the other positive.
Which other positive? Oh, right here, that is an accident. Yes, thank you. Yes. Sometimes I make mistakes. Thank you for pointing them out. Please don't hesitate. If you see something that looks a little bit wrong, yeah, that's a mistake. And that should be a minus sign right there, not a plus sign. Thank you. Good catch. Other questions? Okay, the reason I bring this up specifically is because taking the derivative of the natural log of y comes up kind of a lot when we think of y as a function of x. And so when we take the derivative of the natural log of y, it's usually going to be 1 over y times the derivative of y times dy dx, or y prime, whatever you like. Specifically, it's going to come up when we try to find, yeah, we should do this. If I want to find, say, for example, the derivative of 4 to the x. Has your teacher talked about this yet? Like something where the base is not just e? Okay, there's a couple ways to go about this. I have a strong preference. I will show you both ways, but I will show you the way that I think is better first. So the way we usually do this is by starting with setting y equal to 4 to the x. And then typically when we have some variable in the exponent, we want to get it out of the exponent. Ooh, I'm gonna give me a quick moment over here for 1 second. I just want to make, there's something I want to make sure everyone's okay with, and just trust me. What's the derivative of 5 times x? It's not a trick question. That's exactly what you think it is. It's 5. Because 5 is a constant and x, right? The derivative of x is just 1. In a similar way, what's the derivative of, say, I don't know, pi times x? Right. One more, just for the fun of it. What's the derivative of 2 to the 75th power times x? Right, 2 to the 75th power. All these numbers in front of x, even though some of them are kind of funky, are all just constants. Okay, you'll see why I said that in just a moment. I'm going to take the natural log of both sides here. The natural log of y is equal to the natural log of 4 to the x power. And now we're going to use the rules of logarithms to bring that x down. So we can say that the natural log of y is equal to x times the natural log of 4. And now we're finally going to take the derivative of both sides because we can. We differentiate both sides. Again, not just assuming, but actually seeing right here in the first step that y is a function of x. So when we differentiate, we know that y is some function of x. So we have to use the chain rule. We have to use implicit differentiation here. The derivative of the natural log of y is 1 over the stuff times the derivative of the stuff. Okay, here's why we just did all that. What's the derivative of x times natural log of 4? Well, even though it's kind of funky, just like pi and 5 and 2 to the 75th, the natural log of 4 is a constant. Right? There's no variables there. If you plug it into a calculator, it gives you a number. It gives you the same number every time you plug it into a calculator. It's like 1.18 or something. I don't know, 1.38, I think. I don't know. But that's a constant. Just like this and this and this. And when you have the derivative of a constant times x, you end up with just the constant. I'm going to write 1 times natural log of 4 just to be extra explicit about it. Now I'm going to solve for the derivative. So the derivative dy dx, if I multiply both sides by y, is going to equal y times the natural log of 4. And finally, I can plug back in the fact that y is equal to 4 to the x. So it's actually the case that the derivative is equal to 4 to the x times the natural log of 4. Or writing it out in the most informative way, the derivative of 4 to the x is equal to 4 to the x times the natural log of 4. And in my opinion, this is definitely the best way to do a problem. It's called logarithmic differentiation. When you take the natural log of both sides of an equation, so you can simplify one side of it and then differentiate both sides and then solve for y prime. It's a pretty common tactic. Let's look at a couple more examples. Yeah. So let's make it a little bit more complicated. Let's say I want to find the derivative of I'm covering things up here. Apologies. So I want to find the derivative of 5 to the x cubed. I'm going to do the same thing. I'm going to say y equals that function, the natural log of both sides, differentiate both sides, solve for y prime. We are going to stop doing this in a second because we're going to see a pattern. But let's start. So we're going to start with y equal to 5 to the x cubed. We're going to take the natural log of both sides. And the point of that, or actually I should say, plus it again. The reason I'm doing that, the thing about this equation that's telling me to do that is I am seeing a variable in the exponent. That x in the power, so I don't know how to deal with that other than by getting it out of the power. And the way I know how to do that is by taking the natural log of both sides, because the natural log of something like this allows me to bring down the power and say, okay, I'm gonna have x cubed times the natural log of 5. Right, this x cubed gets to come down in front. And now I can differentiate both sides. The derivative of the natural log of y, just like every other time, is going to be 1 over y times the derivative of y. And I do prefer to write y prime, it's just easier to write. But dy dx is perfectly fine if that's what you prefer. Okay, the derivative of x cubed is 3x squared. The derivative of x cubed times a constant is 3x squared times that constant. Or as I like to say, constant multiples just hang out. They don't go away, they don't change, they just stick around. Whereas constants on their own, like in this problem up here, when we took the derivative of 7, it was 0 because it wasn't multiplied by some function of x. But constants that are multiplied by functions of your variable, they stick around, they hang out. All right, we're ready to solve for y prime. So y prime is going to equal y times 3x squared times natural log of 5. But then finally, if we plug back in the fact that y is equal to 5x, 5 to the x to the third, subbing that back in for y here, and we're getting that y prime is actually equal to 5 to the x cubed times 3x squared times the natural log of 5. So you don't want to do this every time you have some atypical base, meaning some base other than the natural base e. E is the best, right? If I asked you the same sort of question, but it was the derivative of, say, e to the x cubed, we could all do that without kind of really doing any of all of this. We have in fact, I want you all to do it. Find the derivative of e to the stuff. I know we haven't done a lot of these yet, but remember the derivative of e to the x is e to the x. The derivative of e to the stuff, wow, I've already given it away. The derivative of e to the stuff is going to be e to the stuff times what? Right, the derivative. When it's stuff and it's like, what do we multiply by? It's always going to be the derivative of the stuff. In this case, 3x squared. Now notice the similarities. The derivative, in fact, let me write this over here. The derivative of 5 to the x cubed is 5 to the x cubed times 3x squared times the natural log of 5. The derivative of e to the x cubed is e to the x cubed times 3x squared. Really like times the natural log of e, because that's 1. These are the same. The only real difference is that one of them has a base of e, and the natural log of e is just 1. And one of them has a base of 5, and the natural log of 5 is just the natural log of 5. So the general kind of pattern here for finding the derivative of some other non-natural base to a function of x, in fact, let's just do one. If I want to find the derivative of, say, 6 to the sine of x, well, I know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of 6 to the stuff is going to be 6 to the stuff times, thank you so much. And then I also need to throw in a natural log of 6. Yeah.
We would have to add anything that's on basketball, right? But we would have to add the.
What I think you're saying is if your base is not e, then you'd have to also multiply by the natural log of 6 in this case, or the natural log of 5. Yes, you would. But if the base is e, you never need to write this part here that I wrote. The natural log of e is just 1, and you never need to write that part. But what I'm trying to exhibit here is the similarity between whether your base is e or whether your base is something other than e. It's kind of cool. So why don't you all try this one on your own? Find the derivative of 3 to the x squared plus 1. Without doing all this logarithm different, just write the 3-piece answer. covariant. I want to walk around, like, what would you do? But there won't. Okay. Here's what I hope you're getting. So just like the derivative of 6 to the stuff was 6 to the stuff times the derivative of the stuff times the natural log of 6, the derivative of 3 to the stuff is going to be 3 to the stuff times the derivative of the stuff times the natural log of my base. And that's the whole story. Let's talk, well, question. No?
Yeah, on like a test, if you do it that way, we need to show.
So on a test, I believe that as long as your base is a constant, 3, 5, 6, whatever, it's perfectly fine to use this formula. In fact, this formula does occur in your textbook. Look, that's exactly where I was going to go next. So let's I want to kind of revisit, sorry, I'm going to keep my notes in order here, all of our derivative formulas for exponential functions. So I'll remind you of the two we already talked about. The derivative of e to the x is e to the x. The derivative of, I'm going to say stuff, but I'm going to write f of x. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. And now we have a different version, which is very similar, but a little bit different. If our base is not e, so some other constant, I'll set some restrictions on in a second. Let's say our constant is a. The derivative of a to the x is also a to the x, but we have to multiply by the natural log of a. Technically, I also have that being true here as well, right? If I multiply by a natural log of e, that wouldn't change anything. It would still be the same formula. And then the very general version is the derivative of a to the stuff, just like we did in the previous two problems, is a to the stuff times the derivative of the stuff times the natural log of a. And really, what I should actually say is that this last formula here encompasses all the other three. This is true if a is equal to e, or if a is equal to 2, or if a is equal to 7, or if a is any positive base that is not equal to 1. Those are the restrictions on your bases. Your bases have to be positive. You can't have like -4 to the something power. It's just not a good function. And your bases can't be 1 because 1 to any power is always 1. So it's not exponential, which is boring. So yeah. So for example, just as a quick comment here, no one should ever be asking you to find the derivative of, say, like -2 to the x. That's not something we deal with. They could ask you, the derivative of -2 to the x, because the negative is then just happening at the end, right? This is going to equal -2 to the x times the natural log of 2. It's kind of like you took the function, just multiplied by -1. So don't get confused, right? -2 in parentheses to the x is not good. It's terrible. Try graphing in Desmos, you'll see that you just get like weird little points and you don't like get a nice curve at all. Whereas -2 to the x is your exponential function flipped over the x-axis. It's a nice continuous differential and everything. So love it. Yeah, are we there yet? Let's see what time is it. Okay. We should at some point also talk about exponential growth and decay. Okay, yeah. Let me say a couple more things about this, first of all. There is another way to do this. I personally like memorizing this formula. I think it's not too terrible, but there is another way to approach it. If, for example, I wanted to find, say, the derivative of 7 to the tangent of x, I could do it this way. I could say, okay, it's going to be 7 to the stuff times the derivative of my stuff, which is secant squared of x, and then multiply by the natural log of 7. That is certainly one way to go, my preferred way to go. But you can do something different. Some people will teach. I'll be honest, I learned it this way for many, many, many years. And then, I don't know, maybe 5, 10 years ago, I saw someone teach it. I was like, oh, you can do it this other way? That's weird, but it totally works. So here's a different way. You can rewrite this derivative of 7 to the tangent of x as the derivative of e to the natural log of 7 to the tangent of x. You can always rewrite any function as e to the natural log of that function, because e to the natural log undo each other. So e to the natural log of some stuff is just the stuff, but now watch. That tangent, I have the natural log of 7 to the tangent power, and that tangent can come down in front of the natural log. Still in the exponent. So now I can rewrite this as the derivative of e to the tangent of x times the natural log of 7. Well, we do know, or we do need to know, the derivative of e to the stuff. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So watch for just a second. The derivative of e to the stuff is going to be e to the same stuff multiplied by the derivative of that exponent. The derivative of tangent times a constant is secant squared of x times that same constant. Now let me ask you all, is this answer the same as the answer I got doing it the other way? Well, let me ask you a better question. Do they look exactly the same? No, they don't. But are they exactly the same? Yes, they are, because if you'll notice, 7 to the tangent is the same as e to the natural log of 7 to the tangent, which is the same as e to the tangent of x times natural log of 7. Or in other words, this part right here, this e to the tangent of x times natural log of 7 is really just 7 to the tangent of x. So I can rewrite this as 7 to the tangent of x times secant squared of x times the natural log of 7. So that's a way some people like to do it. I don't like to do it that way personally. I feel like I'm adding in an extra step of complication, but for some people that really works. So if that's you, do it the way that really works. I'm definitely I don't know, an equal opportunist when it comes to math. Like, as long as what you're doing is correct and works for you, that is totally fine. You do not have to do it the same way as me. Now, if you're getting to the right answer by doing wrong things, then I will try to put you on the right path. But if you're getting to the right answer by doing things that are correct, even if they're different than the way I've talked about it or showed about that I like, it's totally fine. Okay, so we've talked about exponential functions with different bases. Now we're going to talk about logarithmic functions with different bases. And we're going to see a very similar pattern occur. Just like, in fact, I'm going to say, just like when we take the derivative of an exponential function with a different base, we end up multiplying by the natural log of that base. But other than that, the formula kind of remains the same. The same sort of thing's going to happen with logs of a different base, except that we're going to end up dividing by the natural log of the different base instead of multiplying by it. Let's see some examples. Again, we're going to take the long way first, and then we'll talk about shortening it up. So let's say we want to find, let's say we want to find the derivative of log base 6 of x to the 8th plus 3x squared. Before I do anything, I'll point out that I can't really simplify this in any useful way. This is addition here, so I can't break it up into two logarithms. To really do this the longer way, we have to write it as an equation. So sometimes someone's going to ask you to take the derivative of something, and the onus will be on you to first say, oh, I'm going to write this as y equal to a thing, and then manipulate both sides of that equation to get where you want to go. So I'm going to rewrite this as y equal to log base 6 of x to the 8th plus 3x squared. And then I'm going to remind myself, I'm trying to find dy dx. Okay, let's rewrite this logarithmic equation as an exponential equation. Whenever I do that, I always ask myself, what is my base? Is it y, is it 6, or is it x to the 8th plus 3x squared? You guys know, I know you know. How do I read this? I read this as log base 6, right? Right, that's why, in fact, that's why I encourage you all, when you don't just say log 6 or whatever, really say the word base. It'll help you remember, oh yeah, the 6 is the base, the thing that's lower down in the base right? Like you think like music, like the treble's up here, the bass is down there. The bass is 6, it looks lower, it is lower, it's the bass. The base is 6, the power is y, and it's equal to the argument. Some people will say, I will say, a logarithm is an exponent. And what they mean is that when you take the log base 6 of this, you get the exponent that you would need to get from 6 to that. So 6 to the thing you're looking for is equal to x to the 8 plus 3x squared. And now we're going to differentiate both sides. We just learned how to take the derivative of 6 to the y. So we're going to differentiate. Okay, let's be careful. The derivative of 6 to the stuff is 6 to the stuff times the derivative of the stuff times the natural log of 6. On the right-hand side, we don't have to be quite so careful. We just have functions of x. We can differentiate those not too terribly. The derivative of x to the 8th power is 8x to the 7th. The derivative of 3x squared is 6x. Second to last step, we're going to solve for y prime, just like we do every time we do it like this. So if I want to isolate this, I'm going to divide both sides by 6 to the y and natural log of 6. So I'm going to get y prime equal to 8x to the 7th plus 6x over 6 to the y times natural log of 6. I would really prefer that my answer didn't have any y's in it. We would always prefer especially if you're starting off with y as a function of x, that usually means we should be able to write our answer for the derivative as a function of x without having any y's in it. And we can. We can rewrite this as, well, look, 6 to the y is equal to x to the 8th plus 3x squared. So I'm just going to replace the 6 to the y with what it's equal to, which is x to the 8th plus 3x squared. And then that natural log of 6 is still in the denominator. For the sake of comparison, actually, let me write one more thing before I say for the sake of comparison. So I would just go back and reframe and say, we can then see that the derivative of log base 6 of x to the 8th plus 3x squared is 8x to the 7th plus 6x divided by x to the 8th plus 3x squared times the natural log of 6. Or as I would like you to say in your head, I certainly say this in my head, the derivative of log base 6 of some stuff is 1 over the stuff times the derivative of the stuff divided by the natural log of 6. And then we scrunched it all together. Let me show you something to compare it to before we get too into the weeds here. If I was to take the derivative of, say, the natural log of x to the 8th plus 3x squared, it would be 1 over the stuff times the derivative of the stuff. And then I would write that stuff on the top if I wanted to as 8x to the 7th plus 6x divided by x to the 8th plus 3x squared. The only difference between this one here and this one here is that in the first one, I have an additional division by the natural log of 6. I don't have that here, although I could, if I wanted to, write in an additional division by the natural log of my base, and my base is e. So natural log of e is 1. So really, same idea. It's kind of weird. I'm not gonna lie, it's kind of a weird formula. Let's look at one more example before we kind of make the bigger connection here. So let's say, yeah, let's do that. So let's say we want to find the derivative of, I'll write it more nicely. Let's say we're going to find dy dx given y is equal to log of e to the 5x plus secant of x. I didn't write it because I don't want to, and I'm lazy, and it's typical. But what is the base I didn't write? Yeah, exactly, 10. When you guys say something, you do have to say it a little bit loudly, because sometimes my hearing is not good. So yes, please say words, so James can hear them. All right, so we're gonna do this one again the long way. But actually, let's think about doing it the long way, but also what the answer is just gonna be. If I was gonna find the answer in what's eventually gonna be the shorter way, here's the connection I'm usually making. I'm not really paying attention to the base 10. I'm saying I know the derivative of the natural log of some function is 1 over the stuff times the derivative of the stuff. And I know that for a different base, I'm just gonna add in, or I should not add the bad word there. I'm going to also divide by the natural log of that base. So here, I know that the derivative of natural log of this would be 1 over all that times the derivative of all that. The derivative of e to the 5x is e to the 5x times the derivative of 5x. The derivative of secant of x is secant of x times tangent of x. But then since my base is something other than e, my base is 10. I know I didn't write it. I'm gonna write it. So my base is other than e, I also need to divide by the natural log of 10. Now, I really don't want to write all of this divided by the natural log of 10. So instead, what I'm going to do is just say I'm going to multiply by a 1 over the natural log of 10. That looks kind of ugly. If you wanted to make it look pretty, you could write it all like e to the 5x times 5 plus secant of x times tangent of x divided by e to the 5x plus secant of x in parentheses times the natural log of 10. And I already kind of failed at making it look pretty, because if I was really trying to make it look as pretty as possible, I would put the 5 before the e to the 5x. Doesn't really matter, but that would be standard practice. So that's what I'm thinking my derivative is going to be. It's going to be 1 over the stuff times the derivative of the stuff divided by the natural log of my different base. But let's actually go back and do it the long way, just to kind of verify for ourselves one last time that this is really what you're going to get. So if I was going to write y equal to log base 10 of e to the 5x plus secant of x, I could then rewrite it as my base of 10 raised to the y power equal to e to the 5x plus secant of x. And then we can differentiate both sides. If you really wanted to, you could take the natural log of both sides first. Oh yeah, that's right. There's totally that other way of doing it too. Sorry, there's like 10 different ways you can do these things sometimes. So I'm trying not to over inundate you with many ways of doing the same thing. I'm trying to give you what I think is the easiest way. We differentiate both sides. The derivative of 10 to the y is going to be 10 to the y times the derivative of y times the natural log of 10. The derivative of e to the 5x plus secant of x, as we've already seen, is going to be e to the 5x times 5 plus secant of x tangent of x. And then just like in the previous problem, we're going to solve for y prime. So we're going to get y prime equal to all this stuff. And I am going to write it as 5 times e to the 5x, because I do think that looks nicer. Plus secant of x times tangent of x, all divided by 10 to the y times natural log of 10. But then, hey, we know that 10 to the y is equal to e to the 5x plus secant of x. So we're going to substitute that back in for 10 to the y. And we're going to get that our actual derivative here is equal to 5 e to the 5x plus secant of x times tangent of x divided by 10 to the y, which is really e to the 5x plus secant of x times the natural log of 10. And those are exactly the same. So, long story short, we don't want to do all this work every time we have to take a derivative like this. So we're going to try and do it the shorter way. Just like we had exponential derivative rules, 4 of them, but there's really only, so there's 4 rules I wrote, but there's really only one rule there's one rule to rule them all. Similar thing is true for logarithmic functions. So we have 4 rules, but really the last rule is kind of the one that lords it over the rest of them. So at the very kind of basic level, we have that the derivative of the natural log of x is 1 over x. And then we have the chain rule version, which is that the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then we have the versions with different bases. So if your base is not e, the derivative of log base a of x is 1 over x, and then we also need a natural log of a in the denominator. Or I would say, and we are also dividing by the natural log of a. And then the same sort of thing is true. I want to find the derivative of log base a of some stuff. It's going to be 1 over the stuff. Also the natural log of a all times the derivative of the stuff. And yeah, I know I kind of said that out of the usual order I would have said it in. I would have said the words 1 over the stuff times the derivative of the stuff, and then also divided by the natural log of a. That's how I'm really thinking of it there. You are welcome to write it differently. If you like putting the f prime on top, totally fine. Not what I prefer. Just like before, your base still has to be positive and not equal to 1. Can't have a negative base for a logarithm, it'd be super weird. Why don't you all try, so good to have some practice, try this one. So try doing it the shorter way. Try finding the derivative of log base 2 of x to the sure, x to the 4th plus sure. What haven't we done yet? Cotangent of x. Yeah, cotangent. Good one. Getting those trig derivatives in there. All right. Yeah. So in case you hadn't noticed already, chain rule is kind of always present. It's ever present. Whenever you're taking the derivative of a function more complicated than just, x to a power or e to the x or natural log of x or sine of x, cosine of x, any trig function of x, if your argument is more complicated than just x, you're always having to multiply by the derivative of your argument. That's the chain. So here for the derivative of log base 2 of some stuff, again, that 2 I'm not even really paying attention to. I see logarithm of stuff. And then the derivative of the natural log of some stuff is 1 over the stuff times the derivative of stuff. So that's what I'm going to do here. I'm going to get 1 over the stuff times the derivative of the stuff, which is 4x cubed, and the derivative cotangent of x is negative cosecant squared of x. So I'm just going to subtract cosecant squared of x. And then divided by the natural log of 4, which again, I know I've written it probably the least nice way possible. That's just how I like to say it. If you want to make it look nice, we certainly can. We can write this as one fraction. The numerator would be 4x cubed minus cosecant squared of x. The denominator would be x to the 4th. And I don't know why. So you guys don't let me get away with this mistake. What should I have written there? Yeah, natural log of 2. I think I saw the 4 there instead of the 2 there. That should be a natural log of 2, not a natural log of 4. So then we have on the bottom x to the 4th plus cotangent of x. And we really have to have parentheses around that so that it's all being multiplied by the natural log of 2. It would not be correct if you didn't write parentheses down there around the x to the 4th plus cotangent of x. So that's how we can make it look nice. But really, you should know derivative log of stuff is 1 over the stuff times the derivative of the stuff times 1 over the natural log of your base, which was 2 in this case. All right. I still don't have access to Lee's canvas, unfortunately. I emailed him today. Hopefully he will add me. He certainly added me in the past. I just probably forgot to do it. But what I want to ask you all before we start talking about exponential growth and decay is one more thing I want to ask. Have any of you seen your professor talk about finding the derivative of something like x raised to the sine of x power, where both your base and your exponent have a variable? Is that the yes? Okay, let's do it. Since we're already right, this is the most ideal time to do it. We've already talked about things like this a lot. So this one, unlike the other ones, there isn't really a formula you would want to memorize. There is a formula you could memorize. It's really stupid. I could not tell you. I mean, I could, if I thought about it long enough in my head, I'd be like, okay, this is the formula. But it's not something I have ever dedicated the time to memorize, and neither should you. The process, which you've already seen a few times, of logarithmic differentiation, where you take the natural log of both sides and do all the work, is the better way of doing it. So if you want to find the derivative of something like this, where you have a base and an exponent that both have variables, here's what we do. Start with y equal to the thing that you want to find the derivative. Remind yourself that you're trying to find y prime or dy dx at the end of the day. Right? If you're trying to find the derivative function, you say y is equal to the function, you're trying to find the derivative of y. And then, what do you think I'm going to do next? I have a variable in my exponent. What have I done before to get the variable out of the exponent? Right. I'm going to take the natural log of both sides. That's almost always what I'm going to do. And the reason I've taken the natural log of both sides is so that then I can bring that sine of x down in front of the natural log of x. I'm going to rewrite this as the natural log of y equal to sine of x times the natural log of x. And then we're going to differentiate both sides. But unlike previously, when you would have like something times the natural log of 2, and the natural log of 2 was a constant, here the natural log of x is not a constant. So when we take the derivative of both sides here, what's going to happen is you're going to have to use the product rule on the right-hand side. So I've got the natural log of y, whose derivative is 1 over the stuff times the derivative of the stuff, equal to the derivative of sine of x times natural log of x. Product rule. So the derivative of sine of x is cosine of x, multiplied by, leave the other thing alone, plus, then you reverse it. You leave the first thing alone, and you multiply by the derivative of the second thing. The natural log of x is 1 over x. And then just like with every other problem, we solve for y prime. So I'm going to multiply both sides by y in this case and get y prime equal to y times all of that. Cosine of x times natural log of x plus, I would probably rewrite this as sine of x divided by x. Finally, replace y with x to the sine of x power, because that's what it's equal to. So I'm going to rewrite this as y prime, which is the derivative of x to the sine of x. That's what y prime is. It's the derivative of y. And that's equal to y, which is x to the sine of x, times all of this garbage in the brackets. Cosine of x times natural log of x plus sine of x divided by x. That's how you differentiate something where both the base and the exponent have the variable that you're using. Usually x, but it could be really any variable you want to pick. We're going to do more of these, but any questions before we do more of them? Something I would point out that's true whenever you have something to a power with an x in it, whether it's whether your base is 2 or 3 or e or x or a power or some function of x, is this thing you're taking the derivative of always shows up exactly again. The derivative of x to the sine of x, there's going to be an x to the sine of x. The derivative of go back further. The derivative of 7 to the tangent of x, you're going to get a 7 to the tangent of x times some other stuff. The derivative of 5 to the x cubed, you're going to get a 5 to the x cubed in your answer, and then some other stuff. So whenever you're differentiating an exponential function specifically, it always shows up again exactly as is. And then there's other things you have to end up multiplying by. This is the process of logarithmic differentiation. Take the log of both sides, the natural log of both sides, simplify the side that has the exponent thing, then differentiate both sides, then solve for y prime, and then replace y with what is equal to. So I want you all to try this next one on your own. It's going to take a minute or two. So let's see. Let's say we have. Sure. Let's say we have y equal to. Yeah, let's do that. Let's say we have x squared to the x cubed minus 1 power. I want you all to find the derivative. And you're going to start with writing the natural log of y equal to the natural log. Ooh, x squared is kind of funky. That's fine. That's fine. X squared to the x cubed minus 1. And just because it's a little funky, I want to help you get to one place that's a little bit interesting. So in my next, so we'll do the first 2 steps together, and then I'll let you do the rest. In the next step, what should I be doing? Not ready to differentiate yet. I need to do some sort of simplification, which is going to be bringing down the power. Looks like we're fighting the power. Bringing down the power. The natural log of y equal to x cubed minus 1 times the natural log of x squared. And normally, at this juncture, I would then start taking the derivative of both sides. But what else could I do that would make this even simpler? Well, like everyone's like thinking, like, I think it's this. Half the natural log. No, not really. Yeah, I can also bring down the 2. So I can actually write this as the natural log of y equal to 2 times x cubed minus 1 times the natural log of just x. Yeah, I put the 2 in front because that's right. Order of multiplication. So now what I would like you all to do is differentiate both sides. And yes, on the right-hand side, you will have to use the product rule. If we differentiate both sides, on the left-hand side, we should get 1 over y times y prime, which is, you're gonna see like 1,000 times, right? Just burn it into your brain. The derivative of the natural log of y is 1 over y times y prime. At least if we're assuming y is a function of x, which we almost always are in this class. On the other side, product rule, the derivative of, I'm gonna think of this as one of my functions because I can kind of sneak that 2 into either piece, and I'm just gonna put the pieces next to it. So the derivative of 2 times x cubed minus 1 is gonna be 2 times 3x squared, which is 6x squared. Leave the natural log of x alone. Plus, then you switch, leave the f alone, so leave the 2 times x cubed minus 1 alone, and multiply by the derivative of the natural log of x, which is 1 over x. The rest is algebra, which is said to be reassuring, although it isn't always reassuring. Algebra is still not always easy, but we don't have to do any more differentiating. All we're doing now is isolating y prime. So we're multiplying both sides by y. And I will say, I typically think you can skip writing this step. I'm gonna write y prime equal to y times all this, 6x squared times natural log of x, plus I would probably rewrite this as 2 times x cubed minus 1 over x. And then finally, you're gonna plug back in what y is equal to, which is x squared to the x cubed minus 1. So that finally we can say that y prime is equal to x squared to the x cubed minus 1 times all of this. 6x squared times natural log of x plus 2 times x cubed minus 1 divided by x. Kind of lengthy. But I think if you're comfortable with it, you can skip writing y times all that and just be like, oh yeah, I know that y is equal to whatever it was equal to, and write that in one step instead of 2. But if I skip that step, someone always invariably asks, what happened to the y? So that's what happened to the y, right? The y is just there, and then it's going to replace with what it's equal to. Cool. How much time we got? We got not enough. Never enough. But let's, for a minute, and then we'll talk more about this on Thursday. Let's talk about section 4.6, which is exponential growth and decay. Let's look at an example. So here's what I think of as a typical exponential growth or decay problem. In 1960, the world population was approximately 3 billion people. And in the year 2000, the world population was about 6 billion people. So the question we're going to ask is, when assuming a model of exponential growth, which is always the assumption we're talking about exponential growth in K, when will the population reach 9 billion? And again, I better write it because I have to write it. Assuming the population grows exponentially. I'll just point out here, the answer is not going to be 2040. Right? It's not that the population increases by 3 billion every 40 years. It's that the population doubles every 40 years. So when you're thinking about how exponential growth works, or exponential decay works, every same interval of time, the population multiplies by the same amount. Not increases by the same amount, multiplies by the same amount. Think about just for a second, I know the graph when we were graphing the exponential functions on Thursday last week, every time you increase, like when we were graphing, I think I actually have it here. Smart, keep my notes. Do I have it here? Thought I did. No, but it's from the other class. Over here, yeah. So when we were graphing 2 to the x, so to point out, every time you increase by 1, the population doubles from 1 to 2, from 2 to 4, from 4 to 8. So this is not just like something that happens randomly. It is true that every time the time interval increases by the same amount, the population multiplies by the same amount. So I don't know what year we're going to reach 9 billion, but I know that in 40 more years, we're going to reach 12 billion. I mean, it's, again, right? This is making an assumption that's not generally true. But assuming the population grows exponentially, we'd reach 12 billion people by the year 2040. We'd reach 24 billion people by the year 2080. And every 40 years, assuming there was enough resources in space and all the things you would need for exponential growth to work, population would double every 40 years because it doubled in the first 40 years. But the question isn't, what are you going to get in the year 2040? It's how long till you get to 9 billion people? So here's how we're going to figure that out. And here's what we're almost always going to do when you're talking about exponential growth. Okay, we're going to find the model for exponential growth by doing 2 things. By using the data points. So when I do this, I almost always like to make a little table. I got my table of what time is it and how much. So T for time, Y for how much or how many. How many people, how many bacteria, how much radioactive uranium. It's always the amount of stuff you have at a certain time. Also, if I can, I would prefer not to start in the year 1960. I prefer to start in the year 0. So I'm going to say that 1960 is time equal to 0. That's going to be 1960. I'm just going to change my frame of reference. And then 40 years later in the year 2000, that's going to be a time of 40. So when I get my answer later on, I might get my answer being something like time equals 63. Is that the year that we reached 9? No, it's 63 plus 1960. So my answer would be 2023 if my got t equal to 63. So we just have to go back and fix our answer to answer what's actually being asked. And then in the year 0 or at time 0, not year 0, the population was 3 billion. And in time 40, the population is 6 billion. Oh, I didn't say the most important things yet. Our model for exponential growth is y equal to c e to the kt. There's a lot of things to say about this, which I will really, really happily say on Thursday. We don't have time to say them differently. We're going to take these 2 data points and plug them into this model so that we can solve for the constant c and k. We almost always, not always, almost always solve for c first. Usually, if we're given some time equals 0, it's like 0. So I'm going to plug in this data. So y is going to be 3 billion. And t is going to be 0. K times 0 is 0. E to the 0 is 1. So really what I have is 3 billion is equal to C times 1. Or in other words, C is equal to 3 billion. But I don't want to write all those zeros. Sometimes just writing 3 billion. Great. So now we have a more refined model. Our new updated model is y equal to 3 billion times e to the kt. Now we're going to use our other data point to hopefully solve for k. So I'm going to plug in 6 billion for y and 40 for t. Solving for k, I first have to get rid of this coefficient here. So 6 billion divided by 3 billion is going to be 2 equal to e to the 40 times k. Now I'm going to take the natural log of both sides. So the natural log of 2 is equal to the natural log of e to the 40 times k. Most people skip this step. Specifically skip writing natural log of e to the something because we know that the natural log of e to the whatever is just going to be the whatever. I like to say that the natural log of something and the e to the something undo each other. So what we really have here is that the natural log of 2 is equal to just 40 times k. And then finally, k is equal to the natural log of 2 divided by 40. And now we can rewrite our model for exponential growth, plugging in both the values of c and the values of k, saying, okay, our model actually is y equal to 4, not 4. Just use new, let's just flip this piece of paper over. Our new model is y equal to 3 billion times e to the k, which is the natural log of 2 divided by 40 times t. This is the answer to the question, how many people are there at any time t? Or write a model for exponential growth at any time t. Sometimes they phrase it weirdly though, like when they say like how many people do you have at time t, they're really saying find the model, find the function. And now we want to answer the question that was asked, which is in what year will we reach a population of 9 billion people? So I go back to my little table here for a second. I'm trying to say I want the population to be 9 billion, and I'm trying to figure out what time it is when that happens. So am I plugging in 9 billion for y or 9 billion for t? Is the population 9 billion or is the time 9 billion? The population. So I'm plugging in 9 billion for y, and I'm solving for t. We're almost out of time here, so let's do this real quick. That's terrible, James. This should not be an equal sign there. That's awful. Try that again. 9 billion for y and solving for t. Divide both sides by 3 billion. 9 billion divided by 3 billion is 3. E to the natural log of 2 over 40 is t. Again, we take the natural log of both sides. So the natural log of 3 equals the natural log of e to all this stuff. Again, I would encourage you to normally skip that step and just say that we have the natural log of 3 equal to the natural log of e to the all this is just the all this part. So the natural log of 2 divided by 40 is t. And then finally, multiply both sides by 40. Divide both sides by natural log of 2. And then that answer is not super meaningful. Like, I don't know what that number is. 40 natural log of 3 divided by natural. So then I would actually get a calculator and say like, oh, wow, that's really funny. I didn't actually look at the answers on my hand here, but the number is actually 63. It's really, I didn't plan that. So this is approximately 63, which means that the actual answer is the year 1960 plus 63, which is 2023. So if these numbers were accurate and if the population actually grew exponentially, we would expect to have reached a population of 9 billion in the year 2023, which I'll point out we did not. Thank goodness. All right, we'll stop there. Next, on Thursday, we'll continue to talk about exponential growth and decay and kind of other interesting things to see, be aware of. Also, I should mention, this is not the only way of writing the model. This is generally my preference is writing it as C e to the KT, but there are other ways of doing it.